Hello, Algebra 1 students, and welcome back to Topic 8, Polynomial Operations and Factoring. Today's lesson 8.4, and it's called Special Polynomial Cases. It's going to be one more day of multiplying polynomials. So this is really going to be the last day that we focus on Goal 22, and then starting on our next lesson, Lesson 8.5, we're going to finally move on to Goal 23, which is all about division of polynomials, or more commonly known as factoring. So let's go ahead and do a little opener first. Your goal is to multiply both of these out, combine your like terms, and we'll see what we get for an answer. Ready, set, go. All right, well, as you go through and do this, I'm just going to use arrows for this first guy. In fact, I'll use arrows a couple times just so we can get used to it. We'll be using the box a bunch later on, so nice to practice both methods. X times 3x gets me 3x squared. X times 6 is positive 6x. Here's negative 3x and negative 6. And then, of course, we combine our like terms. The only two like terms I hear are 6x minus 3x. That's 3x. And then minus 6 at the end. All right, let's go ahead and try this next one. Now, this next one, you have a couple options. Option 1 is you could multiply these two together. Option 2 is you could multiply those two together. Or even option 3 is you could multiply these two together. We have these three factors here, 3x minus 1 and x plus 2, that are connected with multiplication. So we need to go through and multiply. And usually we go left to right, so I might as well do that. So the first thing I'm going to do is distribute the 3 to the x minus 1, not to both, just to one of them. This gives me 3x minus 3 in parentheses, and then x plus 2. Once we're here, we're going to double distribute like we did earlier. 3x times x is 3x squared. 3x times 2 is, of course, 6x. Negative 3x and negative 6. In fact, this is looking a little bit similar to me to a problem I think we just did. 3x squared plus 3x minus 6. Actually, we got the exact same answer. Is that a coincidence? Well, actually, it's not. You might notice on problem 2 that if I had chosen to rewrite this a little bit first, if I had chosen to put the x minus 1 first, then the 3, then the x plus 2, and then I went through and distributed the 3, and this would become x minus 1 times 3x plus 6. And isn't that exactly the same as the problem we did on problem 1? Yeah. So this problem was actually, problem 2 is the same as problem 1, just in disguise. Now, you should have algebra tiles by this point, and as before, you should have 6 of those x squareds, 10 of those x's, and 25 of those 1's. If you don't, ask your teacher. Make sure you have the same amount all the way through the class period, because you'll be asked about the number at the end as well. And we're going to go ahead and move on to today. The big focus for today is to look for patterns. Pattern-wise, we are going to start with our algebra tiles with a pattern that looks like this, where we have x minus a number, x plus, and then the same number, x minus something, x plus something. The first thing I'd like you to do, though, is to model this with your algebra tiles. So you can just do this with your partner, maybe in between your two desks or on a single desk, right? You're going to go ahead and set up those tiles. For example, x minus 2 times x plus 2, I have set up for you. It looks like this, right? We have an x up here, minus 2 1's, and then on the left side, x plus 2. Okay, so that's the outside. You would, of course, have to multiply or figure out what fits to find the inside. Then, once you've modeled that on your desk, you need to go through and actually multiply all of this out to see what you end up getting. Combine your like terms, make sure they match. At the end, right, read our question. Normally when you multiply two binomials, a 2 by 2, you get 4 terms as an output. And a lot of times those 4 terms simplify to 3 terms, right? Isn't that what we did on the opener? I got 1, 2, 3, 4 terms. These simplified, stayed the same, stayed the same. So it seems like we were able to simplify to get 3 terms from 4. Let's see if that happens here as well, a binomial times a binomial. So algebra tiles, try it on your own, see if you can answer the question. Ready, set, go. All right. you are back. Well, the first thing I'm going to do is I'm actually going to go ahead and copy my 3 algebra tile pictures from the other page into this page, just with a little bit of mathemagic here, and then we will talk about both the algebra tiles and the work needed to be shown. Now, you should have been able to outline your tiles the same way that I did here. I, again, just copied and pasted them over so you didn't have to wait for me to do everything. But I think it's really important to see the visual here of what's happening. So I'm going to go ahead and show you what the insides of each of these look like. And we've discussed before, if you're drawing this, you didn't have to here, but if you're drawing it, a lot of times it's pretty easy to go through and just extend these lines down anywhere there's a little crease or gap so that we can see the shape that everything's making. Right? And you could do one here and over here. So now we should be able to see the inside pretty easily, right? This first shape is an x squared, that's a blue one. And then let's just work our way down. We know a positive times a positive, this is area, stays positive, so that'll be one of your green x's. This one is 2. And then we know a positive times a negative will actually get you a negative x over here, so I'm going to do this one in red. Same thing over here. And then these ones over here look like it's a negative times a positive for each of them. So each of these are going to be negative 1. Okay. Now, you could, again, multiply all this out, and you should multiply it out. It's good practice. But let's see if we can understand the answer just from the algebra tiles. Right? We clearly have an x squared tile. That's got to be in our answer. And we certainly also have negative 1, but 4 times. So this is going to become minus 4, right? There's 4 negative 1s. But what happens with the x's and the negative x's? Well, you could write them, right? We have 2 x's, they're positive. And then we also have 2 x's and they're negative. But we learned last class that you can take one of these negatives that's right here and one of these positives, and you can actually cancel them out. And you can do this over here as well. So actually the only thing that's left in terms of shapes by the end of this, and I'm going to erase the ones that kind of cancel here, the only thing that's actually left is this x squared that I'm going to shade right here, and then these 4 1s that I'll shade right here. Because if you simplify your answer, we keep an x squared, 2x and minus 2x, negative 2x cancel, and then we keep the minus 4. And that's it. Right? We have x squared, which is clearly in a square, and then we have this minus 4, which is actually also a square, isn't it? This has a side length of 2, and this one also has a side length of 2, right? 2 times 2 gets you negative 4. So we have 2 squares that are left over, 1 positive, 1 negative. Okay, let's try another. So if we go here, I'm going to do that same thing again. We can kind of quickly see what's going to happen here. Nothing too terrible. Let's fill these in. Positive x squared, positive x squared, positive x squared, positive x squared. This guy will be a positive x. Down here we see a negative x. This one will also be negative. I should have kept the positive up here. And then in this lower right corner, this tiny little guy, I think will be a negative 1. But again, we can see what cancels, right? These negative x's at the bottom are going to go ahead and cancel these positive x's that are up over here. If my eraser is going to work, there we go. So that looks pretty good. But then what do we have left? Well, we have this big x squared block. And notice it's arranged in a square. There are 2 going down and 2 going to the right. So here is 1. And this has 1, 2, 3, 4 of those x squareds. And then we also have this cute little minus 1 at the end. 4x squared minus 1. So notice again that the 2 x terms canceled. So in fact, what we did is we took this 2x that was on the side right here, this guy if you will, and then we took 2x up top, we multiplied those together, and that made the 4x squared. Then, to create the negative 1, we took this negative 1 and positive 1, right? Positive 1, negative 1, multiplied those together, and that gave us the term at the end. If you wanted to see this using arrows, right, normally we'd use 4 arrows here. We'd do 2x times 2x, and then we would also do 2x, let's do it in colors, we do 2x times negative 1, and then we do 1 times 2x, and then we would do 1 times negative 1. However, in this situation, two of those end up canceling out. This 2x times negative 1 made a negative 2x, and that canceled with this positive 2x. So in this situation, even though you should multiply all four out, we only had to multiply the firsts and the lasts, and that gave us our answer. So let's try one more, and let's think before we even multiply this out, will that same situation happen? And I think it will, because this really fits the same pattern as the other three, where for the other three we had two binomials that were multiplying together, and they look almost identical. The only difference is that one binomial has a minus and one has a plus. And I think that's the same. 1 minus, 1 plus. And on this last one, 1 minus, 1 plus. In fact, let's maybe even see if we can get the answer with doing less math than normal. Normally, what we've done is these three y's will have to multiply together. That's kind of corresponding to this guy times this guy. And if I show this out here, it's going to be this big square inside. And in fact, with your algebra tiles, I don't even think you'll be able to model this because nobody has. How many are going to be here? Well, 3 times 3 is 9 y squareds. Nobody has 9 of these squared blocks. You guys only have 6 in your set, so definitely becomes a little more difficult. But yeah, this will be 9 of those y squareds, or x squareds if you prefer x's over y's. Then the other thing we're going to need is this little corner down here. Okay, this corner down here is going to be found by using a negative 2 and a positive 2. Negative 2 and positive 2 makes negative 4. Right? We don't have to multiply the others. You could do 3y times 2 and negative 2 times 3y, but because they're the same, though one positive, one negative, they'll cancel out. And so because this guy cancels that one, we just care about the 9y squared and the minus 4. It's a neat little shortcut. So normally when you multiply two binomials, you get 4 terms as an output, which simplify to 3 terms. Right? And let's just do an opener example really quickly. I'm just going to draw an arrow up here. Right? X minus 1 times 3x plus 6. Okay, and using that opener became 3x squared plus 6x minus 3x minus 6, and it simplified to 3x squared plus 3x minus 6, right? 3 terms. However, in the 3 examples directly above, they didn't reduce to 3 terms, they reduced to 2. And so we should probably take a look at one of those really quickly as well. I'm going to kind of make a wall right here, and we'll do this one down here. We're doing x minus 2 times x plus 2. And let's multiply everything out. Not a bad way to go. X times x is x squared, positive 2x, negative 2x, and negative 4. And when you reduce this very special type of multiplication, these two become 0. And so all we need here is x squared minus 4. It reduces to a binomial. So this pattern, something that we'll need to recognize, occurs when you have two binomials where one is a plus b and the other is a minus b. Whenever you have an a plus b and an a minus b, we call those, and here's a fancy math word for you, we call them conjugate pairs. Conjugate pairs are identical binomials, but one positive, one negative in the middle. The product, multiplication, the product of two conjugates is called a difference. And remember in math when we find the difference between two numbers, for example, if I said, what's the difference between 10 and 6, you'd tell me 4, because difference in math means subtract. A difference of squares. Visually, can you see why we call it a difference of squares? Notice we had a square. You cannot see that at all. That's exciting. Notice you had a square and a square, and those two squares were attached with what operation? With what operation? With what operation? The two squares were attached by subtraction, which is, in math, what we call a difference. So the answer to the product of two conjugates is known as a difference of squares. So let's multiply these and see if we can do them quickly. right? There are 3 of them. The first thing we need to check for each one is it a difference of squares? So we look at one, we say, do they pretty much look the same, but one positive, one negative? Yeah. So the answer to our difference of squares here is just the first ones, that makes x squared. The last ones, that makes negative 49, and that's it. Now again, if you don't remember this, could you multiply the other 2 out? Well, of course you could. Watch what happens if you do it the long way. I'll show you once, but you won't need to do this each time. X times x is x squared. X times negative 7 is negative 7x, positive 7x, and negative 49. X squared, what happens here? Those cancel, minus 49. Same answer as before. We just got to do less work because we recognized it was a difference of squares. Why don't you guys go ahead and try these last 2, see how you do, and once you're done, unpause, and we will chat. Ready, set, go. All right, you're back. We're going to try these 2, and then there are 3 more on the next page that I'm sure you guys will fly through no problem. This one becomes 9a squared minus 16. If you try this one, we have 5 times 5 is 25. C times c is c squared. D times itself is d squared. Negative times a positive is a negative. Now I did mention there are 3 more to go, so why don't you try these last couple to bring in some exponent rules from topic 6 that we keep jumping back to, important for us to know. And then we will unpause and continue on through. All right, hopefully you did all right with these. 2f times 2f, 4f squared. Negative 3 times positive 3 is 9. G times g is g squared. X cubed times x cubed can throw people off. Sometimes people think that's x to the 9th. However, we've learned before with the same base you add the exponents, so it's actually x to the 6th. So I'm getting x to the 6th minus 16. Okay, and our last set, 3n squared times 3n squared, 3 times 3 is 9, n squared times n squared is n to the 4th. Negative 5 times positive 5 is negative 25. M to the 4th times m to the 4th is m to the 8th. Okay, so from here we come to the end of our first pattern that we're looking at this evening, or this afternoon, or this morning, whenever you're watching this. The second pattern, and actually our last pattern, is very much related to this difference of squares. Our last pattern is going to be called a perfect square trinomial. So the first thing we need to remember, and it's something we should be pretty good at so far, is that when anything is squared, it means to multiply that thing by itself. For example, let's expand each term. When you expand each term, it means you write it out the long way. You don't necessarily get the answer unless they ask you to, but we're just looking for the expansion. So 6 squared right here means 6 times 6, right? And so in its expanded form is 6 times 6. Easy enough. X squared means x times x. You get the idea. And the expanded form is x times x. And then x plus 1 squared means, and I'm going to have to write this down below, x plus 1 times x plus 1. Now be careful here. We don't want to say the expanded form is x plus 1 times x plus 1 because we're better at that we're better at PEMDAS than that. PEMDAS would tell us just multiply these two and then add x and 1. Well, that's not what we want to do. We want to do x plus 1 times x plus 1. Now, just a quick reminder, is x plus 1 squared the same thing as x squared plus 1 squared? I'm sure you can see how someone might think those are the same, right? The question they're really asking is, on x plus 1 squared, can you distribute the two? I'm going to put a little question mark here and say that that's equal to x squared plus 1 squared. Is that allowed? Well, let's try something that we actually know how to do, and let's say that x plus 1 squared, well, we know that is x plus 1 times itself. That's true, isn't it? And then we know how to multiply this out too, right? X times x is x squared. Now this is not a difference of squares. We can't use our shortcut here. There's no negative. One has to be positive, one negative. So we're going back to the last couple classes and just multiplying all 4 of these out. X times 1 is 1x. 1 times x is 1x, and 1 times 1 is 1. I see some like terms here. My like terms look like 1x plus 1 more x. That's certainly 2x's. And we're done. So the question remains, are you allowed to distribute a square? Well, I don't think so. I'm pretty certain that x squared plus 1 squared is not equal to x squared plus 2x plus 1. They are clearly not the same. This one has an extra 2x. Now, everything I did in blue here is correct. That's what we've been doing. So this guy right here is correct. The one in red is wrong. And in fact, the one in red, and we're going to put this in here, kills puppies. Remember, we did this a couple classes ago in topic 7. We said if you distribute a square to addition or subtraction, it kills puppies. And this one gives us a little bit more insight as to why that is true, right? Not the killing puppies, but why you're not allowed to do it. This is the correct way. We spent a few classes learning it. Trying this shortcut in distributive property as a shortcut does not give us the same answer. Therefore, we cannot distribute. So now that we know how we're supposed to do it, let's try to understand the name. The name, again, is a perfect square trinomial. Well, we're going to have to multiply each of these out, and correct me if I'm wrong, I think this is as easy as just distributing the square, right? Wrong. Hopefully you glared at your screen and said, Mr. Grant, don't kill puppies, because you'd be right. We don't want to distribute that too. Instead, the right first step, and you're going to want to do this for each one, is to write this as that binomial times itself. And I'll do the same thing for the rest of these. Now, we're not done here. Right? At this point, we are going to model these with algebra tiles because we want to have a good idea of what the reasoning is behind the name. And also, we want to make sure that you don't make a mistake and think this is a difference of squares. It's very easy to confuse this right here with, come on screen, you can do it, with this right here. They almost look the same, but on a difference of squares, there's a minus and a plus. But on this perfect square trinomial, there's just a plus and a plus, or a minus and a minus. If one of those was the other sign, then it'd be a difference of squares, but it's not. So, two things to do. First, model with algebra tiles, just showing you, right? This would be our first one, x plus 2 times x plus 2, and then fill in the middle. And second, make sure you go through and multiply all this out so that you can get an answer and simplify it. As before, you're going to pause the video. When you unpause, I'll go ahead and paste in my drawings as well, and we'll talk a little bit more about the names. Ready, set, go. All right, I have everything pasted in. Algebra tiles should have looked something like this. And the first thing we're going to focus on is the middle word in that phrase, perfect square trinomial. We're going to focus on the word square. We should remember, of course, that a square is a four-sided object. Has to have lots of right angles in here. And one of the main definitions of a square is that all the sides have to be the same. Sometimes you see them with these little lines through them showing that they're congruent or they're the same there. And so if this side was 5, then this side had to be 5. If this side was 7x, then this side had to be 7x. And in the case of our first one, if the top was x plus 2, then the side also had to be x plus 2. And so I think you'll notice that on each of these, when you design these with algebra tiles, they are all perfect squares, right? They make squares. And that's actually different than our difference of squares up above. Even though there's squares in the name, these guys, I'd argue, are probably not squares because the top and the side are not the same. This side is 2x minus 1, and this one is 2x plus 1. Slightly different. Okay? But if we look down below, these guys are actually perfect squares. Now, when you draw in the shapes, again, I think it really gives you a nice visual about what's going on here. Right? To create your answer, take a look at what's happening. We are going to get a nice square at the beginning, and we're going to get a nice square at the end. 1, 2, 3, 4 is 4, right? We basically did 2 times 2, right? 2 times 2, which is 2 squared, or 4. and then we have the x squared to start. However, to find the rest, we had 2x's down here and 2 more x's over here. So we had 2x's plus itself plus 4, which gives us x squared plus 4x plus 4. And I think you'll find that this pattern begins to repeat. So if we look at our next one, we've got our first one, which came from multiplying the first together, that's x squared. And we have this last guy down below. This last guy is created by doing -1 times itself. So this answer is -1 squared. Now, I realize that -1 squared is +1, right? This area down here is +1. And I should make this a positive color for you guys. But then what happens for the rest? Well, we have a -1x and another -1x. This middle term is either adding or subtracting to itself. So in fact, you could double that middle term to get x squared minus 2x plus 1. Let's look at 2 more and see if this can become a little bit more clear. Okay, we're doing something like this here. We have, and I'm going to drop it like this, I think. We have this square to start us off. This square is created by doing 2x's times 2x's. So the inside of the square is 2x times 2x, or 2x squared. So we know that the inside will be 2x squared at the beginning, and also this guy at the end was that -1 squared. -1 squared at the end. Now we should be able to see that 2x times 2x is actually 4x squared, and we talked before about how -1 squared is actually +1. What about the rest? Well, there's, -x and -x, so that makes -2x's. And then we know by being a square that if there are 2 -x's here, there have to be the same up here, so there's another -2x's. And so our final answer will be 4x squared minus 4 of those x's plus 1. Once more, just for fun, stick to that blue. So something like this. And over here, okay, we know the inside of the square is 2x and 2x. So I know that if we think about this square, I'm not really distributing, but we know there is going to be a 2x squared in there. We also know that this 2 here is going to create a 2 by 2 square at the bottom right. And so I can actually know that this is going to end in 2 squared. That kind of takes care of the 2 there. Now these last ones are a little bit trickier, and so I'm going to go ahead and kind of subdivide over here and do the same here. I know that there's going to be 1, 2, 3, 4 x's, right? 2 of those 2x's makes 4x's. And then I know that there's going to be a second set of 2x's, or of 4x's. I can actually just double that. I know that there's 2 of these that are going to happen. And so that gives us 4x squared plus 8x's plus 4. And I think actually that pattern has happened every time. This first term is squared. It makes a square at the beginning. This last term is squared. It makes a square at the end. And then there are going to be double the number of x's in the middle. And notice that those x's in the middle are actually created by doing 2 times 2x. These two together gave us this, and then there are 2 of them. Now you certainly don't have to memorize this. We're actually going to go through a formula to do this in a second. Most everybody is still just going to multiply, 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 and that's great. It gives you the right answer. However, math is again all about recognizing patterns, and especially once you move into that programming side of things, and programming is huge these days, it is all about patterns. How can you apply a pattern so that no matter what numbers you're using, you can still spit out the right answer? So without further ado, let's get some conclusions in here. Based on your modeling with Algebra Tiles, why do you think we call the problems from the previous page perfect square trinomials? Well, the perfect square is easy, right? We have the same base and height for, and I'm just going to say the algebra tiles. By the way, there is another reason these are called perfect squares. We're going to dive more deeply into that later on. And then trinomials are because our trinomials, so the answer I'm going to say is a predictable trinomial. There's always three terms and they fit a specific pattern. So let's actually write out that pattern really quickly. So if you have a plus b squared, the pattern we discussed on the previous page, and it's again, if you're like, ooh, this is kind of weird, it's okay. There's still a way that you can do this without the pattern, and it's pretty easy. But the pattern was, if you had a plus b times itself, we knew that we would have a squared. That was kind of that upper left, and I'll even draw you a picture over here. I'm going to do something like this. We knew that the upper left would be whatever a was squared. And we also knew that the lower right would be whatever b was squared at the end. Looks pretty good. Then there would be these guys over here. Okay, so what ends up happening is you have a and b as your sides, so this area is AB. And then you have a and b as your sides. This area is also AB. How many ABs do you have? Well, you have two of those ABs. And so, really what you do is you multiply these two together and throw a 2 in front, and now you've got your formula without having to do any distributive property. It works very, very similarly for these minuses, and I'm going to again draw you a nice little picture over here. So we are going to have this upper corner a squared, easy. This lower left corner will technically be negative b times negative b, so it'll be negative b squared. However, when you square a negative, what happens? It becomes a positive, doesn't it? So a lot of times people will just leave that off and just make it a positive. Okay, but then we have a here and a here. A times a gave us a squared. A times negative b will be negative ab. A times negative b will be negative ab. And how many negative ab's do we have? We have two of those negative ab's. Okay, so often, and actually I should write this better, we have two of those negative ab's. There we go. Oftentimes, though, you'll see this written as a squared, and they'll just say, well, a positive times a negative is a negative, and then they'll keep the 2 out front like so. And then they'll also say anything negative squared will become positive, so they leave that off. This is probably the more common way you see it written. Okay, now, I did promise that I could give you a different, maybe even a faster way, potentially a faster way to do this, but a way that's maybe definitely less confusing. However, it's important to try these patterns. So let's see if we can do it. Okay? Apply the pattern for a plus b squared to x plus 8 squared. All right, I'm going to try to color coordinate this up here if my colors cooperate. So we're going to have x plus 8 squared. X in blue, 8 in yellow. And I'm going to show you where that came up above as well. My x is going to be like the a here. Okay, we see those? So I know that pattern-wise, everything else that's not an a or a b will be the same every time. So I'm actually going to fill that in ahead of time. Something squared plus 2 times something plus something squared. I'll even put the little times in here so we can remember that there's numbers that go here. And then you'll notice that the a, in this case, at the beginning is like the x. So it's going to be x squared, and there's going to be an x in the middle. Then we also had b. b was this guy and this one. So b is 8, right? And so it's going to be an 8 and an 8. And then we simplify. X with parentheses squared is just x squared. 2 times x times 8. Do multiplication in any order. I'll do 2 times 8 first. That'll get me 16, and the x is going to tag along. And then 8 squared is 64. Ta-da! We just did x plus 8 squared. Let's try one more, and then I'll show you that this doesn't have to be this confusing. Okay, our second pattern, a minus b squared. I'm going to, again, in black, write over everything that will be the same every time. And then color coordinate. We have a, which is here, and then we don't actually deal with the negative. The negative is already included in the problem, so I'm just going to do the b like so. Let's write out this pattern. I should have included a and b. There we go. So we have something minus something squared. That's going to equal something squared minus 2 times with those two guys in the middle, plus something squared. Filling them in, a in this case is 3y. And so that'll be 3y squared minus 2 times 3y, and that's it for the a's. And then we have the b's, which is just the 10, not the negative. The negative's in the problem, so just the 10. And that'll be a 10 here and a 10 at the end. Simplifying this down, 3y squared, we can distribute the square here. There's no addition or subtraction. That's 9y squared minus. Let's do all the multiplication. 2 times 3 is 6. 6 times 10 is 60, and the y just tags along. And 10 squared is 100. Pretty cool, huh? Recognizing that pattern. Now, again, I don't want you to feel overwhelmed and be like, oh my gosh, this class just took a crazy turn. It didn't. It just took a small little detour, and we're going to jump back on the regular path shortly. Now, if you wanted to do x plus 8 squared without using this formula, could you? Of course, we've been doing this for days now. X plus 8 squared is just x plus 8 times x plus 8. When we multiply, x times x is x squared, x times 8 is 8x, 8 times x is 8x, and 8 times 8 is 64. If you combine those like terms, can you see it's the same thing that we got up above? Potentially even with less hassle or a headache. Right? Not bad at all. So you can still multiply it out. The idea of those looking at these patterns is that we should realize that you can apply a pattern to mathematics to get the same answer no matter what. And sometimes that's easier. Other times it's not. Okay, let's finish off class today with a little bit of geometry. Now, you should know at this point from middle school how to find the area and perimeter. Remember, perimeter measures the distance around the outside. Area measures the amount of stuff on the inside of most two-dimensional shapes at this point in life. However, you may have forgotten how to do that, so let's maybe refresh your memory, huh? So we have rectangles, squares, triangles, trapezoids, circles, and I'm going to draw a few of them just so you have some examples here, right? We have a rectangle. We know it could look like this. A rectangle could also look like this, or you could have, of course, a square, right? Squares have all the same sides. Rectangles have two different sides. A square is a type of a rectangle, but either way, looks something like that. Great. And we usually label these with a base and a height. I like base and height like so. You could also say that they have like a length and a width. That's the same thing as base and height. For a square, because they're all the same, a lot of times you'll just see squares with base and base or height and height. It's the same letter though. In fact, you could even just say it's x and x if you'd like. So to find the area of these, we usually just take these and multiply, right? Area is base times height. Or you could say it's length times width. Or because they're the same here, for a square, I'm just going to put this at the end, for a square you can just say it's the base squared, right? The base times itself. Nothing bad. Now, perimeter, though, is where people get all tripped up. Because perimeter is how long it would take you to walk around the outside. What's the total distance? And for that, we're actually going to add each of these up. And so I'm just going to work with the base and height one. Base, height, this is also a base, this is also a height because they're the same. To add them up, we do the base plus the height plus the base plus the height. However, base plus base means we have two bases, and height plus height means we have two heights. So sometimes you'll see the perimeter like that, twice the base plus twice the height. All right, triangles, lots of different ways to draw a triangle. One of the easier triangles you'll get is called a right triangle. It's a triangle that has a right angle. That makes this the height and this the base. However, any triangle can have a base and height, right? If you had something that looks like this, then my height is always drawn at a 90-degree angle, like so, and there's still a base. Now, what we should also remember, though, is that technically any triangle can be made into a rectangle. And so that means a triangle is half of any rectangle. And so to find the area of a triangle, you just find the area of a rectangle, which is base times height, and then you divide it by 2. A lot of times you'll see that as base times height, with a 1/2 out front. 1/2 times base times height. They mean the same thing. The perimeter for a triangle can be quite a bit trickier because you don't always have all the sides. And in this case, for now, I'm just going to say the perimeter is just add the sides. So if you have 3 sides here, maybe we'll call this side C, you would just do B plus H plus C. A trapezoid. A trapezoid is another form of a rectangle. The definition of a trapezoid, though, is it's a 4-sided shape like a rectangle with only one set of parallel sides. Notice for this rectangle we have parallel sides, which you'll see with those arrows. Those are parallel. And then we have a second set of parallel sides. A trapezoid can only have one set. So let's draw those parallel sides first. Here is a set of parallel sides. There we go, much better. The other 2 sides can't be parallel to each other. They'd have to run into each other if you extended it. So the most common trapezoid you see looks like this, because if these lines kept going, eventually they would run into each other, wouldn't they? You could also see a trapezoid that looked something like this, right? Either way, though, there's going to be some sort of height measured from between the 2 bases, and there's going to be what we call base 1, and I'm using a little 1 there, a subscript 1, to show it's different than base 2. In order to find the area for this, we basically, and you'll get more of this in geometry, make the bases the same. We take a little bit from this base, and we give it up to this base right here, so it turns this into a rectangle. Take a little bit from here, move it up here, and we end up with a rectangle. So when you have 2 different numbers, these bases, and you want to make them the same, what you're essentially doing is you're finding what we call the average, or the mean. And to find the mean of 2 things for the base, we add them together and divide by 2. So the area of a trapezoid is base times height. However, to make the bases the same, we do base 1 plus base 2 divided by 2. That's going to give us an average base. And then we multiply by the height. It's base times height. Sometimes people will take this 2 and they'll move it out front and they'll say 1/2 of base 1 plus base 2 times the height as well. Last but not least, we have circles. Yay, circles! For circles, okay, we hopefully know what a circle looks like, right? It looks something like this, and there's usually a point in the middle. Okay, this circle can have this R right here, which is a radius. That is halfway across a circle. Or it could have this line that goes all the way through, which we call D for the diameter. Right? The diameter runs all the way through the circle. And so you can see the radius. If you double the radius, it becomes the diameter. Now, circles have a special name for the perimeter, the distance to travel around the outside. They call it the circumference. And these are 2 formulas you again learn in middle school. The way you find the circumference is you do 2 times, well, no, we're not going to do it that way, sorry. You just take pi, 3.14, whatever, right, and multiply it times the diameter. And that's it. And that's actually the basis of how pi was discovered, because if you divide the diameter to both sides, those cancel, and it tells you if you measure the distance around a circle and divide it by the diameter, you should get exactly pi. And so people started to realize thousands of years ago that if you measure any circle, no matter how big or small, and then measure the diameter and divide them, you get pi every single time. So we have this pi times d. However, because the diameter, you could also double the radius to get a diameter. Sometimes you'll see this as times 2r, or even 2 pi r. All of those are fine. The area, though, is the tricky one. The area is pi times your radius squared. So there's a square that comes in. All right. So for the rest of class, we're just going to use these formulas here, and we're going to apply them to different situations, right? We're going to go through, we're going to find rectangles, squares, triangles, trapezoids, and circles. What I'd like you guys to do is start trying them. Okay, your goal is to find the perimeter and area for the given rectangle or square for this one, right? And for the perimeter, and it might help you to draw a picture too, right? You're just going to find the actual perimeter, the actual area. Okay, the area here we know is base times height. They gave us the base, they gave us the height, so the area is 15. It's not bad, right? The perimeter, here's my cute little picture. We have a base of 3. Oops, that's not a good picture. Second try. We have a base of 3 and a height of 5. Well, that's 3, that's also 5. To find the perimeter, we would just do 5 plus 3 plus 5 plus 3. Or you could say there are 2 5s and 2 3s. That's 10 plus 6, that is 16. And that's that. Some of your problems will have x's in them, which means your answers will have x's in them. We say that those answers are in terms of x. They don't have to be perfect, right? They're not going to get nice number answers. There'll be x there. So try each of them. If you get stuck anywhere or you have questions, unpause, skip to that point, and we'll see how you're doing. Ready, set, go. All right, let's jump into B, and this shouldn't be too terrible. I'm actually going to start with the area here, but I will draw you another adorable little picture. Here's my square. Each side is 2x. So I'm going to go ahead and put those over here. Okay, to find our perimeter, we just have to add up all the sides. However, we should realize that each side is 2x, and there are 4 of those 2 sides. So I'm just going to do 4 of those 2x's, which gives us a perimeter of 8x. Our area is normally the base times the height. However, they're actually the same. So you could say it's 2x times 2x. Or you could also say it's 2x squared and distribute the square. Regardless, though, you should get an answer of 4x squared. All right, last one. Let's see if we can do it without a picture this time. The perimeter, there are going to be 2 of these bases. So there are going to be 2 of these x minus 3's. And then there are going to be 2 of the heights, right? 2 sides, so 2 of those x plus 3's. Then we're going to have to multiply this guy out. 2x minus 6, right? We're trying to write these answers in standard form. That's why I'm writing everything out. This becomes 2x plus 6. I think a few things cancel here, right? Minus 6 plus 6. And 2x plus 2x gets us a perimeter of 4x. What about the area? Well, our area here is going to be x minus 3 times x plus 3, base times height. And when we have these 2 binomials, normally you would do 1, 2, 3, 4, or the box method. But you might also recognize that this ties into what we learned today. This is a difference of squares, 1 negative, 1 positive. And for a difference of squares, we can just multiply the first to get x squared, and the last to get negative 9. And you're done, because in a difference of squares, these negative 3x's and positive 3x's will cancel out. All right, let's move on to triangles. I think we're getting the idea here. They did ask us to find the perimeter. We are not going to find the perimeter here. That actually doesn't make a lot of sense, so don't even worry about that part. And we are just going to find the area. Okay, so area equals, I'll remind you up here, I like to put the 1/2 out front. 1/2 times the base times the height. Some people put this over 2 though. I like multiplying by 1/2 instead of dividing by 2. It's up to you. So let's start with our first one. Area equals 1/2 times the base times the height. And realize that instead of putting the dots here, I put these in parentheses. That both saves me from having to put the dots and reminds us that we should group things we substitute in parentheses. So because I'm substituting 2 in here, we do want to group that in parentheses. It saves us from not correctly multiplying at the end. Now, because you can do multiplication in any order, you could do 1/2 of 2 and then multiply that by 6. Or you could do 2 times 6 first. That's 12, and then 1/2 of 12, which is 6. Let's try another. Area equals 1/2 times the base times the height. Okay, and so again, 2 options. I'll go the other way. 1/2 of 2x is 1x this time, and 1x times 4 is 4x's. This one's in terms of x. Part C, area equals 1/2 the 2x times the 4x. And I'll go the other direction this time. We'll do 2x times 4x. We know 2 times 4 is 8, and x times x is x squared. Half of 8x squared is 4x squared. Last one. Area equals 1/2 times the base times the height. Now with this guy, I'm not actually going to distribute the 1/2 here first because this one in particular would give me 1/2 x, and that sounds gross. So really 2 options here. Either you can multiply everything out here first. You'll have to do that multiplication eventually. Or you can be really clever and say, well, instead of putting the 1/2 here, I can put it at the end, and you can actually distribute the 1/2 into the end. I imagine most people didn't think of that though, so I'll do the more common way, which is we're just going to do the multiplication of the 2 binomials first. So, parentheses, 2 times 4 is 8. This gives us 4x. This gives us another 4x. And this last one at the end gives us 2x squared. Finishing this off. I'm not going to distribute the 1/2 first. I'm just going to write the parentheses in standard form. I'll do the 2x squared first. 4x and 4x. There's 2 4x's. That gives me 8x and a plus 8 at the end. Now let's distribute the 1/2. And you'll notice that conveniently, every number in here is even. It's divisible by 2. So when we do half of each of those, life is pretty good. Half of 2x squared is 1x squared, or just x squared. Half of 8x is 4x, and half of 8 is 4. Ta-da! Okay, next up, trapezoids. We're just finding the area here, and I'm going to remind you of that area formula each time. Again, I prefer to put the 1/2 out front, base 1 plus base 2 times the height. I'm going to do that 3 times just so we can see what's happening here, and it gives us a nice visual for the replacement. There we go. So let's start substituting in. 1/2. My base 1 is 3. My base 2 is 9, and the height is 2. We follow PEMDAS here. A is already isolated, so I'm going to do the 3 plus 9 first to get 12. And half of 12 is 6. And 6 times 2 is 12. Right? We should have seen that because half of 2 really cancels out and just leaves us with the 12, but that's okay. Next one. In terms of x this time, devious. Who came up with this problem? X plus 5x, and the height is 3. Okay. Well, x has a 1 in front. 1x and 5x is 6x's. Half of 6x is 3x, and 3x times 3 is 9x's. Last one. Okay, base 1 this time is x, base 2 is 2x, and then the height is 1/2 x. Whoa, this one's getting weird. Alright, let's do the inside first. 1x plus 2x is 3x times 1/2 x. We might want to be clever here, and I might want to say that this is 3x over 1. This is x over 1. I'm going to just kind of multiply things straight across. 1 times 3x is 3x. 2 times 1 is 2, right? We can multiply fractions with uncommon denominators. That's fine. 1 times x is 1x, and 2 times 1 is 2. Right? So can you see what happened? I took these two to create this guy, and then these two to create that one. Once we're here, let's continue multiplying straight across. 3x times 1x, well, 3 times 1 is 3. X times x is x squared. And 2 times 2 will give us 4. So our area is 3x squared over 4. You could, by the way, also write this as 3/4 x squared. All right, last one, circles. Find the area and circumference of each given circle. Leave pi in your answer. Now, that's a very common thing to do because, and this is just like square roots, right? And I'll compare this on our calculator over here. But when we did square roots last unit, when we got something like the square root of 2, kind of a gross square root, right? And I'll remind you, if we try the square root of 2, that's 1.41 whatever. We didn't want to write that decimal. That's gross, and you have to approximate it. You'll stop writing that infinite decimal eventually, so we just leave it as the square root of 2. pi is the same thing. Pi is also irrational. Pi 3.141 goes on forever, right? We don't want to write all of this. We don't want to write just part of it because that becomes a little inaccurate. So instead, we just leave the symbol pi in our answer. It's actually less math for us, which is nice. So to finish this off, okay, we know that the circumference is either pi times the diameter, but in this case they give us radius every time, so let's do pi times twice the radius. Twice the radius is the diameter. So pi times twice the radius in this case is 4. That becomes pi times 8. And traditionally we write the number in front of pi, in front of that irrational number, and so we say the circumference is 8 pi. Okay. Area-wise, we know that area is pi times the radius squared. Shouldn't have done it like that. We should have said pi times the radius squared. There we go. And we know in this case our radius is 4. 4 squared is 16. And again, we write the 16 in front of pi just because that's what people enjoy doing. Now, I'm not going to rewrite these formulas every time. I don't want to run out of room. So for our next one, circumference is pi times twice the radius, and my radius is 2x here. So circumference is pi, 2 times 2 is 4x, or it's going to be 4x pi. Let's work that area. Area is pi times my radius squared. Notice the square has to go outside of all of that. We are allowed to distribute the square here. There's no addition or subtraction. So we know 2 times 2 is 4, right? 2 squared is 4 rather, and x squared is just x squared. So finishing this off, 4x squared pi. Last but not least, we know our circumference is pi times twice the radius. So pi times twice this x plus 5. Can you see my mistake? This looks like it's just 2x, doesn't it? But I need to multiply 2 times x plus 5. I need that extra set of parentheses in here. 2 times all of that. So pi, and then I need to distribute the 2. So that gives us 2x plus 10. Or reorganizing, this is 2x plus 10 pi. Let's do the area. Area here, pi times my radius squared. And then I just distribute the square, right, to finish with pi times x squared plus, let's see, 5 squared. Or do I? Did I just kill puppies there? I think I did, huh? Yeah, we cannot distribute a square. Oof, hopefully you caught that. Yeah, we can't distribute a square. So instead, you can recognize that this is a perfect square trinomial and use the formula from earlier. Or if you don't remember that, and I don't blame you, you can just do x plus 5 times itself. And to do that, we're just going to double distribute or use a box if you would like. X times x is x squared, x times 5 is 5x. I know there'll be another 5x. It's that perfect square trinomial. 5 times 5 is 25 at the end. So, finishing this off, we have x squared plus 10x's plus 25 times pi. So, thank you for sticking through this with me. I know it's kind of a longer video, and I apologize for that. But we're really getting that practice in. We really hit this multiplying polynomials pretty hard because when we get into the last part of this unit, which actually is like 6 or so lessons, all about division, you really need to be comfortable with the multiplication. So I'm excited for you to join us again for lesson 8.5, which will be factoring using a greatest common factor. You'll definitely want your factoring sheet ready. It's really going to help you out. Hopefully you're finding success in this unit, and I will see you next class.